Now the problem is that despite those two great ideas, you can run into the following situation. Let's say you are station A, okay, and you want to say talk to station B, which is an access point, and then someone else across from you in the Starbucks or in a hotel room, hotel lobby, want to talk to this same AP. Okay. Now, if you both talk at the same time, actually you will collide. Okay, but let's say your sensing range has only this radius, which is the same as your, let's say, transmission range. Okay, so you cannot sense the existence of C, and when C is talking, actually, you can't even hear it. Okay, so you may just start talking again, and then B suddenly get confused. So this is the problem, that two stations in Wi-Fi may interfere, but they do not sense each other, and this is one of the fundamental limitations that says that if you want to use random access and yet sensing range is not the same as interference range, then you have a problem. So how can we tackle this problem? Now, so far we have used no explicit message passing yet. Now we're going to need a little explicit message passing. You have to send some control signals, what we call RTS, CTS, okay? Request to send and clear to send. So the basic idea is that the sender, okay, when you want to send something, you first send a control packet, a tiny one called request to send. Okay. And then upon a small listening interval, the receiver will send another control packet called clear to send. And then after another little interval, you can start sending. Now, why would this work? It works because when you send a request to send, okay, everybody in your transmission range hears this. So B hears this. And then B will then send a clear to send. And everybody that B can talk to can hear this, including yourself and others who might want to talk to B. Okay, now I'm assuming a symmetric transmission range. B talk to C's range the same as C talk to B for now. Now C will then say, oh, I didn't ask to send something, but I get a clear to send signal. That means somebody else is going to send something, so I'll refrain from talking. Okay. Again, all these discussion here on TCP assume that the network elements obey the protocols. If they actually try to trick the system, then you need some other kind of game theoretic analysis. All right, so now A says that, hey, I send RTS, then I got a CTS. That means I'm clear to send because all potential interferers I cannot hear have got this CTS, and they will refrain from sending. So that's the smart idea of RTS, CTS. Use a little sequence. Okay, so there's the overhead. You have to pay the overhead of spending this much time just doing control signaling in order to guarantee that the data will not be colliding, even when you cannot sense somebody. So this is the famous hidden node problem. C's hidden node to A or vice versa, and RTS CTS solution of that problem. Of course, it's not perfect. For example, the RTS packets may collide. So it does not completely solve the issue, but helps quite a bit. All right, now we're going to try to understand CSMA built upon the ideas 1, 2, 3 that we just mentioned. Okay, wait and listen through carrier sensing. Use randomize the binary exponential backup upon collision, that is no acknowledgement back, and use RTS CTS explicit control messaging if needed. Well, it turns out that analyzing CSMA and Wi-Fi is not that easy. Okay, for a more proper understanding, we need to use something called a two-dimensional Markov chain to specify the protocols, because there's a lot of probabilistic actions, and abstracting those out, like in TCP, our discussion of TCP, would not have enough predictive power. So we need to do some probability theory. And instead of doing a two-dimensional Markov chain, which we would not have the prerequisites in this class, we will do a very basic, a little hand-wavy type of basic probability argument. Okay. The main difficulty here is that the frame collision depends on the action of each radio, as well as the history of binary exponential backoff, so-called BEB. And the binary exponential backoff is in turn coupled with the transmission decision. Should I transmit or not? Which is again probabilistic by each station. So because of this complication, even this hand-wavy simplified version of argument would take a little derivation, okay, through basic probability theory. Now the basic idea we want to do is that we want to look at two probabilities. One is the probability, okay, of transmission at a given time slot. The other is the probability of collision. And then we'll try to relate these two probabilities and derive two equations and solve two variables. Now let's go into the detail here. First, a little notation. Let's say we want to derive the performance metric of CSMA, random access. Denote that by S, okay, which is really the average throughput. That's the average number of bits transmitted successfully over transmitted, okay? A time slot divided by the average length of a time slot. There are different kinds of time slots, and this is an average notion, okay? So it's average number of bits successfully transmitted over the average length of a time slot. That is S that we want to derive, and we want to see how does S depends on different parameters in the problem. Okay. We're going to use P sub t to denote the probability of transmission. In fact, I should say probability of at least one, it could be more, transmission in the entire Wi-Fi network. Okay. And then we use P sub S to denote the probability that the transmission is successful given a time slot, and that means there must only be one single transmission conditioned on someone transmits. So it's a conditional probability. And now we're going to use tau to represent the probability that a particular station, say your phone, transmits at a given time slots. The difference between tau and PT is that PT is the probability that someone in the whole network transmits, and this is for each individual. And let's assume that each individual station acts independently, okay? And now we're going to define some time slots. T, okay? We say TB is the time slot when there is basically back off. Okay, everybody's backing off, nobody's transmitting. T sub C is the time slot where there is a collision. Somebody transmitting, but turns out more than one. And TS is this one and only one transmits, so there's a successful transmission. So TB, TC, TS are a little different. We'll walk through a numerical example in the next module. So these are the main notation. Now we can look at the basic quantities here. Okay. First of all, the chance that there's no transmission at all, the probability is 1 minus P sub t. Okay. And the time slot associated with that is TB. The probability that there's some transmission but it doesn't go through is PT times 1 minus PS. And the time slot for that is collision time slot. The third one is that somebody transmit and actually there's only one, so it's successful. PT times PS, and then the corresponding time slot is T sub S. So this expression is the denominator for S. It's the average length of a time slot. Okay, it's this quantity. So we have this quantity now. We want to now get the numerator, the average number of bits. Well, what is the average number of bits? Well, it is PT times PS. That's the probability that you have a successful transmission. Okay, somebody transmits, and condition on that, there is a successful transmission. Multiply that together, you get successful transmission probability, and then you times the payload, denote that by L. Okay. So now we have the overall expression that we need. Okay. This is the numerator, and this is the denominator. So we divide this expression by this expression, and that is our S. All right, looks like we're done. Well, this is just a start because we have not yet derived the expression of PT and PS. So what is PT? PT is the probability that somebody is transmitting. So that equals to the probability that if you say tau is the probability that one station is transmitting, 1 minus tau is the probability that a station is not transmitting, because they're all acting independently. You raise it to the power n because you multiply itself n times. N is the number of stations in this Wi-Fi network. Okay, say it could be 5 at your home and 20 in a hotspot. Okay. So this is the expression that says no one is transmitting. And then 1 minus that is the probability that at least someone, could be one, could be more, is transmitting. Now, this expression, 1 minus, bracket 1 minus some probability to the power n for a crowd of n, is another type of wisdom of crowd. If you remember wisdom crowd as a factor of n, and back then in lecture 5 or 6, 5, we said that this is what we call a multiplexing gain. Okay, because of independent of actions of the crowd, you can have a factor of n reduction of some error metric. Now this is another type, what we call, instead of multiplexing gain, a diversity gain. It says because of independent actions, we actually have this 1 minus some probability to the power n shape of the expression. All right, that's a little detour. So this is PT. Now what is PS? Times PT. That's the probability of successful transmission. Okay. Now for each individual station, that means you have to transmit, but no one else transmits. So tau multiply 1 minus tau n minus 1 times. And there are n of these independent actions. So the total probability is this. So now we have both PT and PT times PS. And therefore we can substitute into this expression. We got the numerator, we got the denominator, we're done. But wait a moment, we actually don't know what is actually the tau factor, right? And that's the hard part, right? Tau really depends on the history of the exponential backoff. That determines the transmission decision. So as long as we can find expression for tau, we'll be done. We can then substitute into these expressions for PT, PS, and then substitute into expression for S. All right, so give me tau now. Well, one thing I do know is that the probability of collision, let's express that quantity as C, okay? Let's assume that this probability C is independent of which backoff stage you are at. Okay, have you backed off once? Have you backed off twice, 3 times? Let's say we're independent. It's independent of that. This is our approximation. And under this approximation, we have C equals 1 minus tau to the power n minus 1. Okay, this is the probability at least one of the other n minus 1 station transmits in addition to yourself. Then you have a collision. All right, say, hold on, I want to find tau. Now you express something else, C, in terms of tau. How does that help? Well, we're going to find tau as a function of C now. And then once we have a tau as function C, C is a function of tau, we put the two together, then we can solve 2 variables with 2 equations, at least numerically. So that is the game plan. Find tau as a function of C. The probability that you transmit as a probability of collision. All right, the way we do this is a little roundabout. Here is an interesting Bayesian expression. Okay, third time we're using Bayesian. Haven't used it in a few lectures. The probability that we transmit, okay, we meaning well, a station transmit, times the probability that the station is in certain backoff stage I, condition on that it transmit, is the same as the probability that it is in stage I, backoff stage I, times the probability that you transmit condition that you are in stage I. Because both sides of the equation is expressing the joint probability that you as a station is transmitting and you are in backoff stage I. I just express it in two different ways as in the Bayesian expression. Okay. So now I can use a little shorthand notation. Okay. I'll say this is tau, okay, times the probability that you're in stage I given you transmit equals the probability you're in stage I times the conditional probability that you transmit given you are in stage I. Okay, so now we can say tau therefore equals, or tau multiply pi of tau over p you are transmitting condition you're in stage I equals p of I. Now if we sum both sides across all the backoff stages from the zeroth stage, which is a certain minimum backoff window, okay, W min says that you need to at least back off up to this much, and then you can randomly choose a point in time between now and W min, all the way to the maximum stage of backoff. Now backoff cannot keep on going forever. Okay, at some point you just give up and declare the packet, the frame is lost, and you ask maybe upper layer to help you. So we say there are at most B stages of backoff. And each stage is a doubling of the window size during which you uniformly pick a point to transmit. Okay, so there are two fixed parameters, W min and B. B stages and max, and also you have to at least start by weighting W min number up to W min number of slots. I keep saying up to because the actual transmission time is done in a random way, uniformly sampled between now and the window size. Okay. All right, so back to this expression. This right-hand side is obviously 1 because you are summing over the probability in some stage I across all possible stages. So it got to be 1. All right, so now if we can express Pi condition on transmitting and P transmission condition on I, then I'm done. All right, so that's the roundabout Bayesian detour we are taking. So can I derive a Pi of condition on tau and PT condition on I? Well, let's see. Pi condition on that you are transmitting. What's the probability in backup stage I if you are transmitting now? Well, that means you must have suffered I collisions in the past, and you have one non-collision right now. Okay, so the probability of that is c to the power I times 1 minus c. But this is not a probability, you have to normalize it. Turns out the normalization constant, skipping the derivation, is this. Okay, so this is the expression that we want. Now, what about P condition probability you are transmitting conditioning on that you are in stage I? Well, at this point, you have a certain the value of the backoff counter at the stage I. Okay. Plus, you are using one time slot to transmit. So there's altogether 1 plus T sub I. T sub I is the average value of the backoff counter at stage I. Okay, and you're going to randomly, uniformly pick from one specific time over here. Okay, so it will be 1 over 1 plus t sub I. Okay. Now, what is t sub I then? We just need to find t sub I. T sub I, if you think about it, okay, is really the average value between not weighting 2 to the power I times W min. Okay, this is the minimum window of time you have to wait up to, and you've suffered I stages of collision, so you've been multiplying by 2 I times, so 2 to the I times W min. Okay, plus 0, which is you so happens you choose exactly the current time to transmit, and in between the average value is the half. So this is the expression for Ti, which you can substitute over here, and then you get the probability of transmission condition you are in stage I. All right, so finally we got everything. More strictly speaking, actually, the actual contention window size W is 2 to the raised to some integral power, then minus 1. Okay, so but we're skipping that level of detail here. Okay. So finally, we say plug this expression into Ti, put it in here, you get P of T condition I. You also know P of I condition on T. Now plug those two expressions in here as a function of C, and then multiply by tau, summing over I from 0 to the max number of stages allowed. That should equal to 1. Now that's a complicated looking expression, but nonetheless, now we can finally express tau, okay, as a function after simplification of C. You can try this yourself or look at the textbook, and after simplification, this is what you got. So now tau is a function of C as well as constant parameters, okay, such as W min and B in the network. And C is a function of tau. So this is equation 1. This is equation 2. Put equations 1 and 2 together, you can solve for both tau and C. Actually, we only need tau. Now stick tau into the expression for PT and PS, and then you stick that expression into the expression for S. And finally, you're done in computing the throughput through this approximation. Now, as a function of what? Of the constant parameter in your system, such as the payload, L, okay, the maximum number of backup stages, W, and the minimum backup window, W min, as well as the time slot definition, TB, TC, TS, and finally the number of stations involved, N. All these are constants given by the network to you, and then you can now finally express S in terms of these constants.